It must be evident by now throughout these lectures that the atmosphere has a tremendous influence on the ocean. We saw how the stress of the wind on the ocean creates waves, how the more or less permanent wind system create the great ocean currents such as the Gulf Stream, and how the differential heating of the oceans between the equator and the poles creates the abyssal circulation of the ocean. One thing we haven't spoken very much about is what is happening in the upper 200 meters of the ocean, where in fact energy is absorbed. Now the energy, of course, originates at the sun in the form of radiation. And so the first form of energy that arrives at the ocean is radiation, and a certain amount of this is absorbed, and a certain amount of it is reflected from the surface. Now the absorption of the radiation into the ocean occurs due to the stirring of the waters in the upper few hundred meters due to the action of the winds. And we have the very uppermost surface of the ocean just a few feet heated first, and then the heat is stirred down into the lower layers below it. The ocean, of course, also loses heat to the atmosphere. Part it loses straight by radiation again, and part of this is lost to space. It also loses heat due to evaporation, the evaporation of small particles of water, which rise into the atmosphere, where in fact they can form clouds. If rain falls from the clouds, there is in fact a net transfer of heat from the ocean to the atmosphere. The condensation not only is the most effective means of the loss of heat to the atmosphere, but it also means that we increase the salt content or the salinity of the ocean layers in the upper few hundred meters, because what is evaporated is, of course, fresh water, and this leaves the salt behind it. If we could look at a chart of the temperatures in the Atlantic at 100 meters depth, we would find that it would look like this, with the warmest waters being near the equator and the coldest waters being near the pole. And of course the major circulatory system would move warm waters towards the north along the western boundary. Now let's try and construct a temperature section of the ocean near the equator, taking into account that the abyssal circulation, where very cold water has sunk in the north and flowed along in the abyss. Now what we'd find is here we have the depth of the ocean in meters. That's 100, 200, 300, 400 meters depth. And here we, on this part of the graph, we have plotted temperature. And this would be a line indicating the temperature at each depth. In the very deep water, which has come from the poles below about 1,000 meters, we would find the temperatures less than about 5 degrees, going down to possibly 0 near the bottom. This is determined by the thermohaline circulation. Near the surface, we have a surface layer which is just a few hundred meters thick, where these processes which we have just described are in fact operating. And between the two, we would have a layer where the temperature decreased from possibly more than 18 degrees in temperate regions down to the low temperatures, 3 to 4 degrees of the abyss. And this has been called the thermocline layer of the oceans. And there is a permanent thermocline in existence all over the oceans, and it is caused by the heating of the upper layers of the ocean and the cold water at the bottom, which has come from the poles, which gradually upwells. If we look at this temperature structure in various parts of the ocean, we would find it considerably different. For instance, in the equatorial region, the surface temperatures may be 20 degrees, when in fact they could be higher than 20 degrees, rising to 25 degrees or more. And then the temperature would decrease through the thermocline into the abyssal waters. If we go to the polar regions, where the radiation strikes the Earth obliquely, there of course is not as much heating of the ocean. And in the summertime, we would just find that the surface waters had just heated up very slightly. In this diagram I've indicated they've heated up to about 2 to 3 degrees. And then they would very sharply fall to the very cold waters of the northern areas, which persist in the abyss. Of course, in the wintertime, you must remember this whole northern area, in certain areas, this overturns, and we have our abyssal circulation, which provides the cold water in the equatorial regions. In the temperate zones, northern temperate zones, we have a situation which is in between the two, and there we see a very marked seasonal effect. This would be a picture of the temperature versus depth in an area, say, just south of the Gulf Stream off Nova Scotia, possibly in the northern Pacific. In the wintertime, due to the cooling effect, the water temperatures may fall as low as 10 degrees and gradually drop off. But in the summertime, as the sun moves north of the equator in the northern hemisphere, the ocean will in fact obtain heat, and we'll get a secondary thermocline formed, and the temperatures may rise to 15 to 16 degrees. It depends on the latitude. Now, this is a seasonal effect, and of course it is greatest in the temperate zones. We have this warm upper layer in the summer, and we have a cold layer in the winter. Now, in certain areas, this creates an effect which leads to the creation of ice, the cooling of the surface waters. One area which this can occur is in the Gulf of St. Lawrence. Now, in the Gulf of St. Lawrence system, we have Nova Scotia, Newfoundland, the St. Lawrence River, Quebec. There's a very deep channel, about 400 meters, and into this channel flows salty water from the Atlantic. And out over the salty water flows the fresh water from the St. Lawrence. And this means that we have a layer of fresh water lying over more salty water, and therefore the density of the bottom water is higher due to the salt content. And superimposed on this, we have this seasonal heating and cooling of the surface waters, because the Gulf of St. Lawrence is in a more temperate zone. Here we have a picture of the density and the temperature in the Gulf. The density, this is depth, 100, 200 meters. The density, of course, increases very abruptly as we go from the fresh water to the salty water. In the wintertime, the water cools down and starts to overturn. But this overturning process is limited by this increase in density. So the overturning process will only go to possibly 100 meters or less. In the summertime, we have the warming of the waters as the sun comes north of the equator and there's more insolation. This, of course, is of great interest to the people trying to predict ice in places like the Gulf, and particularly in the Gulf. What then happens is the water is cooled down, and it is cooled down below 0 degrees. But, of course, cooled water is heavier than the water immediate below it, so it will sink. And this process of cooling and overturning goes on in the surface layers until it gets to about this level where the density increases abruptly. Up until this time, although the water is being cooled, it has managed to mix itself down and mix itself down so its temperature doesn't fall too low. But it stops at this point, and then we begin to get ice formed in the Gulf. The process is a little more complicated than I have described, but it is calculable, and this has led to surveys of the Gulf in the late fall to determine exactly what the temperature and salinity conditions in the Gulf are, and then it is used by ice forecasters to forecast when in fact the Gulf will freeze up. Now, a very similar situation appertains in the Arctic Ocean, and it is the reason that there's a permanent ice pack there. And if I may use the globe for a moment to look at the Arctic Ocean. Here we have a picture of the Arctic Ocean. Let's get it round a proper way. We have Greenland, we have Canada, we have Russia, and there's the Arctic Ocean. And there's a major flow of water from the North Atlantic into the Arctic Ocean, past Iceland, and through north of Greenland. Now, there are large rivers running into northern Canada, from northern Canada into the ocean, and from Russia into the ocean. And there is also considerable melting of ice. And this creates a layer of fresh water on top of salty water. And as a result, in the Arctic Ocean, we have exactly the same effect as we had in the Gulf of St. Lawrence. Namely, that we have this water, deep water, which is dense, and we have the fresh water on top of it. And so that the water cannot convect very deeply, and ice will form. And of course, in the Arctic Ocean, we have a permanent ice cover, excepting in some areas, such as in the Beaufort Sea, where it moves a few hundred miles away from the coast. There have been various schemes for the Arctic, such as if one could pump up all the fresh water through the Bering Strait, then deep convection would be able to set in because the Atlantic water would upwell, and then we could remove the ice cover of the Arctic Ocean. But no one, in fact, knows whether that would occur. Even in the Gulf, you do find that the advantage is taken of the fact that we have rather warmer, salty water over this cold, fresh water from the river. And if one puts a bubbler system in, one bubbles the deep water up, and so we get a transfer of, when the water loses heat, we get an overturning of water, and ice no longer forms. Now, up until now, I've spoken mainly about the effects of the ocean on the atmosphere. Now, how about the effects of the atmosphere on the ocean, and does it affect climate, in which we are becoming more and more interested, of course, because of agricultural failures? Well, the answer is the ocean does affect the atmosphere considerably, and in many ways. One of the ways which you may have observed is land and sea breezes, which alternate between day and night. Now, we must realize that the oceans have a tremendous heat capacity compared to the atmosphere, and they can absorb heat due to overturning and convection. The land, of course, can't do this, and if we heat the land up during the daytime, it becomes hot, and then it will cool down at nighttime. And you've probably observed this on a beach. A beach can get very, very hot in the daytime, and at nighttime it can be quite cold to walk on. Well, this creates what's called a sea breeze. In the daytime, under the effect of the sun, the radiation, the land will heat up considerably. And this, of course, causes the air over the land to rise. By contrast, the sea is going to change its temperature very little because of its heat capacity. And as a result, in the daytime, you will get an onshore breeze developing in the afternoon, which is called a sea breeze. At nighttime, the reverse effect occurs. The land cools down because the sun is no longer there. The ocean, which I've again indicated as a cool sea, will not change its temperature very much. And because the land is cold, the water becomes heavy and will subside, and then we will get a movement of air from the land over to the water. And this occurs in many parts of the world. It is more pronounced in some places than others. It also occurs over islands, and it will also lead to the formulation of clouds over islands. And it is caused, of course, by the sea having such a large heat capacity. Now we're also interested, of course, in longer term effects. As you're aware, the climate has changed over the past years, and of course it has also changed in the oceans. The average temperature in the North Atlantic, the average temperature in the Northern Hemisphere is illustrated in this diagram, and one can see that it is gradually heated up from 1880. This is temperature. This is 0, a sort of an average temperature. This is -5, +5. At 1880, the temperature was below an average temperature and is gradually heated up until we come to the period of 1940, when there has been, appears to have been, a general cooling. In recent years, the oceanographers and the meteorologists have become very interested in trying to understand why there are such things as climate change and how they affect the oceans. And this has been, in fact, very difficult to do. There aren't many records, actual records of temperatures which go back that far in time, so a lot of it is speculative. And in fact, there is a large program called the Global Atmospheric Research Program, in which all the nations of the world contribute, which is being developed, but it will take maybe 10, maybe 20 years before sufficient data and knowledge, particularly knowledge of the processes of these interactions, occur. Of course, the type of problem that one finds is that even though one gets this average warming of the Northern Hemisphere's atmosphere, it may not be uniform, and it's certainly not uniform in the ocean. There have been sufficient records of the ocean temperatures generated that we have some idea of what is happening. And in this chart, we have the surface temperature of the ocean between around the period 1780 to 1820, in contrast to the period 1921 to 1938, the difference between the two. This was determined by measurements from ships which were taken in the early days. In the northern part of the ocean, apparently it was very much colder in the early period. In the temperate part of the ocean, apparently it was much warmer. The tropical part of the ocean was a little colder, and in the southern hemisphere we have a warming of 2 degrees again in the southern part of the ocean. Now there have been many of these anomalies plotted, and there are scientists working relating them to changes in the atmospheric circulation. Now not only do we have these changes in climate, it is also evident that the climate of a country is very dependent on its geography. Where does it sit with relations to the oceans? Does it sit on the west side of a continent, on the east side of a continent, and in the northern areas, in the southern areas? And to obtain a picture of the influence that the oceans do have on local temperatures, we will just review our currents very briefly. Earlier in the talk we pointed out that generally the ocean waters are warmest in the equatorial region, and of course we have a circulatory system in the Atlantic, the Gulf Stream carrying warm waters towards the north. These warm waters go over to England, they go past Iceland, eventually they end up in the Antarctic. The southerly flowing current, such as the Labrador current, is very cold. So this made a tremendous difference between the climates of the cities on the and a little way inland on the east side of the ocean and the west side of the ocean. Places such as Halifax and Newfoundland are bathed by the Labrador Current, and so they tend to have rather long drawn out springs, which are drawn out also because of the ice melting in the Gulf. Whereas at the same latitude we have northern Spain, which has a very temperate climate, and we have England, which again has a temperate climate. Even Iceland, in southern Iceland, due to the influence of the remnants of the Gulf Stream, the temperature doesn't fall very much below 6 or 7 degrees in the winter, unless there's an outbreak of cold air from Greenland. And of course, even though Iceland is far north of Halifax, you'll find that if you go to Iceland in the spring, the crocuses are there out and blooming long before they've pushed their head above the surface in places like Halifax. And in other areas we have a cold current sweeping up Africa, a warm current sweeping down past Argentina, and these all influence the climate. They don't just influence the absolute temperatures of the land, they also influence the range in temperatures. In Vancouver, for example, which is on the eastern side of an ocean with the weather moving in from the west, one has the mildest climate in Canada and a temperature range of only about, well, say 30 degrees. Halifax is somewhat colder due to the Labrador Current, and the weather is generally moving away, so the weather doesn't have such an influence on climate, and we'll have a temperature range slightly larger, maybe 50 degrees, whereas in an inland city such as Winnipeg, which is far removed from the ocean, we have a continental climate, and there the temperature changes can rise as much as 70 degrees between the spring and the summer, so that the ocean not only influences the actual average temperature at the year, it influences the range of temperature. We have also other phenomena, and since we have the Gulf Stream coming past Nova Scotia and the Grand Banks, and we have the cold Labrador Current flowing over the banks, this is an area where there is fog created. The winds blow over the Gulf Stream system. There they pick up water due to evaporation, and then they arrive over the areas of this cold water mass, such as the Grand Banks, and very moist indeed. And of course, the water in the air condenses, and one in fact gets these immense fogs. One also gets an area of fog off the coast of California, which is induced by the upwelling, which we described in an earlier talk, of the cold water. Now, we aren't only interested in climates of today, one is interested in past climates, and of course going back hundreds of thousands of years if possible. And of course there have been no measurements in times gone by. The measurements only go back through a few hundred years. But it has been possible to look at the climate of the ocean using certain indicators. One indicator which has been used of past climates is the small animals which live in the surface layers of the ocean. These, the type of animal depends on the temperature. You'll find different assemblages of animals in the colder waters than you will in the warmer waters. And these have been charted for the present day ocean, so the biologist knows his distribution of the fauna. Now these small animals die, and their bodies cascade to the ocean floor, and they do in fact form the sediments of the ocean, which are several hundred meters deep in places. And these sediments can be extracted by coring. This process, in fact, from the ship one drops a long pipe. It is just a pipe with a heavy weight on the top, and plunges it into the sediment and then extracts the sediment, and the geologist can go sections of sediment off, can go back through it, and he examines the type of a small creature which had died and was living there. And then he contrasts this with his knowledge of the temperatures which these small animals live in from today. And he comes up with some sort of crude estimate of the climate of the ocean in years gone by. And this is one, using this type of indicator, this is one such interpretation. This shows the position of what is called the polar front, which is the boundary between the Gulf Stream flowing north in the Atlantic and the cold waters to the north. 6,000 BC, it was up near Iceland. 11,000 BC, it was further south. 13,000 BC, further south again. 17,000 BC, it went across past the Azores. And gradually we have built up a knowledge of the climates of the ocean. Well, as you've realized through this series of talks, the ocean is a fascinating place. And knowledge of the ocean has not come very easy. It's taken many years to accumulate what knowledge we do have today. In the early days, in the early oceanographic expeditions, some of the scientists would go to sea possibly for 2 years on a single expedition and then come home and spend 3 to 4 years, very often more, analyzing the data that they had acquired. However, things have advanced, and one of the things which have advanced is the ships on which people sail. And here we have a picture of a modern oceanographic vessel, the Hudson, Canadian scientific ship Hudson, which was launched in 1961 and commissioned in 1962. The ship is equipped with fast winches. It has comfortable quarters. But even so, life at sea is not easy. In major storms, the ship has to heave to and all work ceases. But even so, the existence of these modern ships, which have been built by countries, Canada, England, United States, and Russia, is greatly advancing our knowledge of the oceans and of the interactions of the oceans with the atmosphere, and hopefully one day we will be able to predict the future.